Hello, dear students. We will start our lecture today where we have ended yesterday. Till yesterday, we have talked about like electrostatic potential and what is your like electrostatic potential difference. And also, we have seen potential due to point charge and due to system of charges. So, we will like continue our lecture today. And yeah, so we have like ended here only. Like example 7 will be started today. So I am covering only the NCERT portion and your physics class 12, and this is chapter 2 of that. Also, it is helpful for your like competition exams also, but it is primarily focused on your NCERT and boards exams. Okay. So let us start here. A charge Q is distributed over two concentric hollow spheres of radii small r and capital R. Okay. So I am talking about this example 7. Here a charge Q is distributed over two concentric hollow spheres of radii small r and capital R, where small capital R is greater than small r, such that the surface densities are equal. So the surface densities are equal here. Okay. Yeah. It means that like if sigma 1 is the surface density or surface charge density here, so sigma and sigma 2 for other surface, so sigma 1 is equal to sigma 2 here. Find the potential at the common center. So we have to find the potential at their common center only. So let's start the question. Here we will assume that Q1 and Q2 the charge on them. So there means there is charge Q1 and Q2 on the surfaces. Q1 is in the inner surface and Q2 is on the outer surface. Okay. So it is also given that sigma 1 is equal to sigma 2. So just apply the formula of sigma 1. What will be that? For this surface, Q1 by 4 pi r square. Here small r square will be there because small sphere is considering here. And here for another surface, Q2 by 4 pi capital R square. Because here capital R, that one sphere is considering. So after like simplifying it, we will get Q1 by Q2 is equal to R square by R square. Okay. Small r square by capital R square. So yes, that is charge on them is distributed in above ratio. Okay. So charge is distributed in this ratio only. Q1 by Q2 is equal to R small r square by capital R square. Or you can find out the Q1 as, so what will be Q1 here? If you have like Q1 by Q2 is equal to small r square by capital R square, then you can find out the Q1 value that will be equal to what? Small r square upon means small r, this one, this quantity upon total quantity. So what is total quantity? Q1 plus Q2. It will be equal to R square by R square. This is proportional to this only. So that is why it will come in the denominator into capital Q. Okay. Because total charge is capital Q. So the part of it that is Q1 is just equal to this by this ratio. Similarly, what is the Q2 here? Q2 will be capital R square upon small r square plus capital R square into capital Q. Okay. The similar reason for this also, that here capital R square is like proportional to Q2. So Q2 will be capital R square upon small r square plus capital R square in capital Q. Okay. So this was your the distribution formula for this question. So let us see that what is the next thing. So potential at center will be what? It will be equal to like summation of potential due to Q1 charge distribution and Q2 charge distribution. So if you substitute the values of the charge distribution here for potential due to Q1 is here, so it will be equal to K Q1 by R, and for Q2 charge it will be K Q2 by capital R. Okay, so you will get what? If you now substitute the value of Q1 and Q2 here, that is equal to what? Your Q into small r square plus your capital Q into capital R square upon, and in the denominator part what you will get? Here you will get like uh, yes, 4 pi epsilon naught into small r. Okay, and the r will be like your small r and capital R are there. So I will separately do that. Okay, let's yes, just see here that if you substitute q1 and q2 value here, what we will get for first value? V is equal to your q1 value is what? Capital Q into small r square upon r square plus capital R square. Okay, now into what? Small r. So this is your q1 value plus q2 value is what? Capital R square into capital Q upon small r square plus capital R square into 4 pi, and k will be common here. So I will take like k common to this. Okay. Yes. So after like now you can take the q common here. You will get k capital Q into r square. Okay. And one r will cancel out here. One r. Here you will get r kept small r upon like small r square plus capital R square, plus here one like q will be like your small r will be cancelled out here, and one r is also here, so it will cancel this capital R. Okay, so you will be remaining with what? Q, and q is common here, so capital R upon small r square plus capital R square. Okay, so this is you are getting inside the brackets. After opening it, you will get it equal to k capital Q into small r plus capital R upon small r square plus capital R square. This is the final expression for what? Potential at the center. So potential at the center is due to both surface charges Q1 and Q2. I hope that you got this problem. So let's move forward and see the next example. Okay, I should delete these drawings. Yes. In the example 8, it is telling that two spherical metal shells with different radii, small r and capital R, are far apart and connected by a thin conducting wire. Okay, so there are two spherical potentials and they are like connected by a thin conducting wire only. A charge capital Q is placed on one of them. So capital Q charge is placed in one on one of them, like on any your sphere. So the charge redistribution so that the same is on each surface. So the charge redistribution is like it is same on each sphere. How much charge is on the sphere with radius of small r? Okay. So here the redistribution of charges like that each sphere get the like same charge. Okay. So we will see this question how that it is done. So their electric potential of spherical shell with a small charge m, small charge q and small radius r is kq by r. Okay. So if you have like this small sphere, so like your electric potential here will be what? K small q by small r. Okay, that is the equation. And when the cells are joined by a conductor, the charge will distribute between them so that they attain the same electric potential. So if you like join it with the conducting wire, so it has the tendency that if you join any two metal uh, spheres or any metal conductors by a conducting rod, then it has the tendency to make their potentials equal at the equilibrium point. Okay, so their potential will become equal. Okay, after some time. Let the charge on yeah, let the charge on the sphere with radius small r be qr. So after some time, I will assume that it has qr charge, and that on the other another charge like it has small q capital R. So this is the charge on them after some time. Then equating the potential gives q r by small r equal to capital Q r by capital R. Okay, so you are like getting it after some time as q r by small r equal to q capital R by small capital R. Okay, this is the like after some time this condition will attain, because I already told you that the potential will become equal after some time. Okay, so the total charge equals the original charge. So you already know that the initial charge was capital Q only, so it must be equal to what? Q R plus Q capital R. Why? Because at the like redistribution point, the charges will like redistribute themselves. So charge can not neither be created nor be destroyed. So the total charge will remain constant. That is why we have applied this equation here. Okay. Now small q capital R will be equal to capital Q minus q small r. Okay. So this is like after constructing this equation, you will get it like this. By equation 1, by this equation, you will get what? Small qr is equal to like capital Q, okay? And your your like QR will be equal to what? If you substitute here, okay? Just a second. I will rub this points. Yeah. So this is by equation 1 only. Here you can see that by equation you have small qr equal to q capital R small r by r. So substitute in this your qr value. Qr value is like this. So if you substitute here, you will get q minus small qr, okay, into small r by capital R. I have substituted qr value only here. This will be here. Okay. So after substitution, you will get the equation like this, and then just see the next point. Yes, solving for q. So after solving for q small r, like if you solve for qr here, you will get what? Qr 1 plus small r by capital R. I have taken qr common here. Capital Q into small r by r. Only this equation you will get after like solving the previous one. So qr will become what? Qr is coming like capital Q small r upon capital R plus small r. Okay, which is the required charge. So this is the required charge after like your charge redistribution. Okay, the value of k is not needed. Starting proportionally is sufficient. Okay, the value of k there is not needed because it will like not provide any sufficient result here. Okay, so it is independent of like capital small k. Okay, so qr is equal to capital qr upon capital R plus small r. Okay, now we will see the next topic, that is what? Electrostatic potential due to an electric dipole. Okay, so till now we have already covered your electric dipole like topic. So that will be used here, and we will like calculate the electrostatic potential here. Previously, we have calculated the electric field for an dipole. Now we will calculate what? Electrostatic potential due to an electric dipole. Okay. So yes. So let us consider an electric dipole consisting of charges small q and capital Q that is separated by a distance to a. Okay. So this we have covered like why dipole is taken like small q capital like small minus q and plus q, and why the distance is taken to a. You can watch the lecture of dipole if you have any confusion in this. So the dipole moment will be what? Q into 2a. Because dipole moment is what? It is the product of charge and one charge and distance between them. Okay. So let capital O be the center of the dipole. Okay. So here see the figure. Okay. So you have a small q minus q charge is here and small plus q charge is here. Okay. And you have the distance between them is 2a. And I will assume the center of this dipole as origin. Why? Because center of dipole is only taken for reference for the distance. And because I have already told you that this is center of mass or center of charge for the dipole. So we will take the distance from like the center of dipole only. So let O be the center of the dipole, P be any point near the electric dipole inclined at angle theta. So P is any point, general point in this plane, which is inclined at angle theta with the like center of your dipole. Okay, it has theta angle. So if this angle is theta, like this angle is taken theta here, so this angle will be what? 180 minus theta. Okay. Yes. Okay. So let O be the we have calculated this part. So let P be the point at which electric potential is required. So P is the point where we have to calculate the electric potential. Now potential at P will be due to what? Minus Q charge also and plus Q charge also, because these are two charges here. So V1 will be equal to what? The V1 will be equal to due to your minus Q charge. So it will be equal to minus Q upon 4 pi epsilon naught upon R1. The distance from like this charge is small R1 here. So why we have taken the distance from minus Q charge? We have not taken from the this dipole center the distance, because we have just now calculated here in individually contribution of each charge. Because I already told you that potential due to system of charge is summation of individual potential due to each charge. That is why we have taken the distance from this charge only, minus Q and then plus Q. So for your minus Q charge, V1 will be equal to what? Minus AQ by small r1. Okay. And for your potential at the point 2 due to positive Q charge, like for this charge, you have V2. That will be equal to what? AQ upon small r2. Because the r2 distance is from here. This charge and P point. Okay. Yes. So after that, we have to just find the potential related to work done by the field. Potential is also related to the work done by field, which we have told like in the previous chapter, your class. Okay. So electrostatic potential also follow the superposition principle that I have explained you. Therefore, potential at P due to the dipole will be equal to what? Potential will be equal to V1 plus V2. Okay. So it will come equal to what? K small q upon into 1 by R2 minus 1 by R1 in the bracket. Because if you add the both terms, you will get this equation. Okay. Yes. Now by geometry, you have what? R1 square is equal to R2 square plus A square plus 2A R cos theta. How this result has came? So let's see why this is like coming here. Just a second. Yes. So here R1 square is what? Your equal to R square plus A square. Okay. What is small a here? Small a is the distance between center and one dipole like charge. Okay, this one. So this is your small a distance. Okay. So we have now just now calculated the value of what? Your small r1. So r1 square will be equal to r square plus a square, and it is plus 2ar cos theta. Okay. Yes. This is why, because if you consider here your like if you have seen studied about the vector calculus. Okay, just a second. Yes, if you have studied the vector chapter of your, so if you have two vectors, like if you have like this vector r1 vector is that. Okay, so this vector is your r1 vector, and this is your what? Small a vector. Okay, this is your small a vector, because the distance between O and A is what? Small a. So this is your small a vector, and this is small r vector. Yes. So if you have like two vectors and their resultant is one vector, so the resultant formula is what? The resultant formula will be like a square plus b square plus 2ab cos theta. Okay. So that is why we have applied this formula here. I will explain you why it is coming like this. If you see here, you have r1 this, and your small a vector is this, and small r this. Okay. So just see here that one second. Yes. Observe here only. R1 square is what? Yes. Here you can see it. This is your R1. Okay. So R1, and this is your small a. This is small a and this is small r. Okay. Now the angle between two vectors, like R1 vector is your resultant. So it will be equal to what? R square plus a square plus 2ar and cos of theta. Okay, why it is so, like why the equation is coming like this? So just to see the figure only. Yes. Yeah. Okay. Yes. So here see the figure. If you observe it, the factor like OA is like this, and this is your small a vector, and your R1 vector is like this. This one is your R1 vector, okay, and this is your small r vector. Yes, okay. So if you now see the like vectors here, R1 is the resultant of these two vectors, small a and small r. Okay. So the angle between like small a, because the angle is only like from like head tail to tail like this. So if you have like a vector like this, and this is your like r1 vector, this one is your r1 vector, this is your small a vector, and like this is your small r vector. Okay, and the angle is here 180 minus theta, but it has taken here, he has taken a theta angle here. So the angle is here taken as this one, because you must see that if you have two vectors like this, okay, and this is resultant, this one is resultant. So you should take the angle what? You should take the angle that is taken from here only, like this one, okay, like this one angle. So that is why 180 minus theta is not the angle. The angle is theta here. Okay. So I hope that you got this point. Now let's calculate this equation, and I will clear the drawing. Okay. Yes. So by geometry also, and by that vector equation, this is coming like this, and your R2 square will be coming like R square plus A square plus 2AR cos 180 minus theta. Okay. This is also due to your vector addition. You can observe here that, yes, this one is your R2 vector. Okay. Yeah. So this one is your R2 vector, and this is your small r vector, like this one, and this is your A vector, small a vector. Okay, like what? This one is your small a vector, and you have already seen that this was your small a vector. So here tail to tail, but here your vector is like tail and head is coming. So we will take like which angle? The angle you taken like your 180 minus theta, because I already told you that tail to tail angle will be covered here. So one if you like transfer it here, so this angle will become 180 minus theta. Okay, and this one angle, if you like substitute this one, you transfer here, 180 minus theta will be there. That is why it was taken 180 minus theta here. And after calculation of this part, this vector part, you will get what? Let's yeah. So you will get the equations as R2 square is equal to R square plus A square minus 2AR cos theta, because cos 180 minus theta is what? Minus cos theta only. So R1 square is coming like R square into 1 plus A square by R square plus 2AR by R into cos theta. Okay. It is coming like after taking the small r square common from here. So your R1 square will come what? If you take a small r square common from here, you are remaining with 1 plus A square by R square plus 2A by R cos theta only. Okay. So let's see the next calculation of this. If R is very, very greater than A, so if R is very greater than A, we can assume that A by R is very small. Okay, so therefore A square by R square can be neglected. So if you have like A by R is very small, like if you have A by R equal to 0.01, So a square by r square will become what? It will become like 0.0001 like that. Okay, it will come like that. So that is why we have neglected a square by r square, because it is coming very less. So there is it is like neglected here a square by r square, and after that you have r1 square equal to what? R1 square is coming equal to small r square into 1 plus 2a by r cos theta, because a square by r square term is neglected. So you are getting this expression. So r1 is coming equal to r into 1 plus 2a by r cos theta to the power half. Okay. And 1 by small r1 is coming equal to 1 by small r into 1 plus 2a by r cos theta to the power minus half. Okay. So how this equation is coming? If you like transfer r1 here and small r here, so you will get this equation. Just cross multiply it. You will get 1 by r1 equal to 1 by small r, and transfer this equation on left hand side. You will get 1 plus 2a by r cos theta to the power minus half. Okay, that is why it is coming like this. Similarly, 1 by r2 is coming what? 1 by small r into 1 minus 2a by r cos theta to the power minus half. This is also coming from second equation. Only minus sign is there due to cos 180 minus theta. Okay. Putting these values in equation 1, we obtain what? So after putting this equation in equation 1, which we have obtained earlier, that is v1 is v net is equal to what? v1 plus v2. Okay. So if you put the values here, you will get k, q, that is common, and in the bracket you will get 1 by small r into 1 minus, that is 1 minus 2a by small r cos theta to the power minus half. Okay. Then minus of 1 by small r into 1 plus 2a by small r cos theta to the power minus half. Okay. I hope that you got this, why it is coming like this, because we have substituted the values of these only, that is r1 and r2 only. Okay. So you will get these equations. So after this equation, you will use binomial expansion or binomial theorem. If you have studied binomial, so you can easily get it. Okay. So if you have like where if x is very less than equal to like 1, okay, if x is very less than 1, so you have the expansion of binomial as 1 plus x to the power n, that is equal to 1 plus nf. Okay, why this is so? So if you have like x is very less than 1, so you have the next terms like 1 plus n minus 1 upon 2 factorial. Okay, after this term I am telling, so you will get like x square. So x is very less than 1, so these terms will be very less also, so they can be neglected. After that, x cube term will come. The x square is very less, x cube is also very less. So that is why we are remaining with 1 plus nx only. So we will neglect the remaining term here. Okay. So yes, 1 plus x to the power n is 1 plus nx. So when we apply this formula here, what we will get? Vp is equal to q by 4 pi epsilon naught small r into 1 plus a by r cos theta and minus 1 minus a by r cos theta. Okay, I will show you how this has come. If you like apply here, Vp is equal to k small q by and small r, because 1 by r is coming common here, you should take it common like outside 1 by r. So apply here 1 plus nx. What you will get? 1 minus minus of 1 by 2, 1 minus 1 by 2 into your minus of 2a by r cos theta. Okay. So 2 and 2 will be cancelled out. So you will be remaining with what? 1 plus a by r cos theta in the bracket. That is why it is coming like this only. And if you calculate this part, this one part, so you will get this expression. You can calculate by yourself. It will come like this only. So after simplifying it further, you will get this. Okay, just open the bracket. You will get like this only. Minus 1 plus a by r cos theta. So here 1 and minus 1 will cancel out. And you will be remaining with what? Q by k q by small r and 2a cos theta upon small r. Yes. So we are getting some final expression here. So yes, just a second. I will rub the like equations. Yes. So what we are getting, PP is equal to Q into 2A, that is Q into 2A here, and cos theta also upon 4 pi epsilon naught into small r square. Yes, that is, what is this? This is equal to dipole moment only, okay, because P is equal to Q into 2A. So it will come P cos theta upon 4 pi epsilon naught into small r square. That is your final expression for what? For your like potential due to dipole. Okay. So with P cos theta, we can write it like P dot R cap vector. Okay. Why? Because P cos theta is like dot product of P dot R cap. Or we can write it like in vector form P dot R cap. Okay. Where R cap is a unit vector along the position vector OP. Okay. So this is the like direction vector. We have added direction vector here. Electrostatic potential at point P due to a short dipole where A is very small, then R is given by B is equal to P dot R cap upon 4 pi epsilon naught into R square. Okay, so what is the value of PP you are getting here? V is equal to P dot R cap upon 4 pi epsilon naught into R square. This is the final expression. This was the final expression, and after adding the direction also, we have written it in vector form. Okay, just a second. So the potential depends just not only on the position vector smaller, but also on the angle between the two position vectors R and dipole moment P. So here you can see that a potential is not only depending on position vector smaller, but it is also depending upon what? Between the position vector smaller and the dipole moment P also. The electric potential due to an electric dipole at P varies inversely with square of smaller. That is, you can also see, and small r square, it is varying with this, and that is the distance of point P from the center of the dipole. So it is the distance from the center of dipole D. Okay, you can see that electrostatic potential is coming equal to this expression. Okay, now we will see some like questions on this, and yeah, just a second. So electrostatic potential is not a vector quantity actually, but here this is the dot product of your vector, so it will give you only magnitude of that. Okay, so it is not any like vector like vector equation. It is the only scalar quantity electrostatic potential, but it is written in dot product of vector because due to dipole moment we have written in this like this equation. Okay, so let's move further and see the what is the next topic. So we have example 9 for us. Let us see that what it says. So an electric dipole consists of two charges of equal magnitude and opposite signs separated by a distance to a as shown in the figure. So here you have minus q and plus q, two like opposite charges that is separated by a distance to a. The dipole is along the x-axis and is centered at the origin. And it is placed on the x-axis, like the dipole is placed on x-axis and center like is at the origin. So we have to calculate the electric potential at point capital P, that is equal to like this point that is on the axis of the dipole. Calculate V at a point far away from the dipole. Okay. So this was the general formula we were getting for electrostatic potential of dipole. And now it is like axial point potential. And for the second point, we have like at a point very far from the dipole. Okay. And so for the point P in the figure, we have V is equal to what? A Q1 by like K Q, this one, K minus Q by R1 plus K Q2 by R2, like R2. Okay. That will be the formula, like superposition formula. So just take the K common here. So if you take common here K, you will get in the bracket like for this charge. Okay. For this charge, you will get what? Q by x minus a. Why this distance? because distance from center of this dipole is what? Small x, and this distance is small a only. So distance from this charge will become what? X minus a. Okay, whole distance is x, this is a, so this distance will become x minus a. So yeah, this is your x minus a, and minus charge there, so we will substitute minus charge here, minus sign. Okay, minus q upon x plus a. So this distance is what? This is a, this is x, so this distance will be x plus a. So after substituting these values, we will get the equation as 2 into k q into a upon x square minus a square. Okay, just take the LCM here. If you take the LCM, you will get what? X square minus a square in the denominator part due to a plus b a minus b equation. And here you will get what? Q into x plus a by taking LCM minus q into x minus a. Okay, and k was outside, like in the brackets, it was outside. So after simplifying it, what you will get? Small k into qx and minus qx will cancel out. Qa plus 2q, like plus qa, you will get 2qa upon x square minus x square. So that is the expression you were getting here, which I told you. Okay, this was the expression. So just like now you can see that you are getting this expression. Okay, for the axial point. If point P is far, that is the answer for first part. Like now we see the second part. If point P is far from the dipole such that x is very greater than a, then a square can be neglected in the terms x square minus a square, and b becomes b equal to 2kqa upon x square. Okay, so what it says, if you have like x distance very large away from the dipole, because a dipole is dipole is here and the point is very far away from the dipole, so you can assume that x is very large. Okay, so in the denominator term, x is very large than a, so x square minus a square can be written in what? In terms of x square only. So your expression will become 2kqa upon x square. Okay, so this is the answer of your what? Second part. So I hope that you got the questions which I have told you today, and also how the concepts of dipole are. And yes, let's move further and see the next topic. Just a second. Yes. So next topic is equipotential surfaces. Okay. So what do you mean by equipotential surface? So any surface which has same electrostatic potential at every point on it is called an equipotential surface. Okay. So if you have like surface here, like you have this surface, and each point has the same potential here, same potential, like P1, 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 everywhere P1. So this surface is called what? Equipotential surface. Okay. So it is a simple concept that surface having equal potential at each point. For a single charge molecule, the potential is given by V is equal to KQ by R. That we have seen already. This indicates that V is a constant if small r is constant. So if the small r is constant anywhere, so your V will become constant also, because V is directly proportional to 1 by R only. So that is why if R is constant, V is already constant, and Q is the given magnitude. So Q is like taking as a constant also. Thus, the equipotential surface for single point charge are spherical surfaces centered at the charge. Okay. So just see here, if you have V is equal to K small q by R, and V is directly proportional to 1 by R. Okay, that is your for what? And like for your point charge. Okay, for a single charge, that is the equation for your potential. Okay, so V is constant and R is if R is constant, so equipotential surface for single charge are spherical surfaces centered at the charge only. Okay, as the equation is like V is directly proportional to 1 by R only. So you will get it like a spherical surface only. Okay. The equipotential surfaces can be drawn through any region in which there is electric field. So we can draw the equipotential surface where electric field is present. If all the points at the same potential in the electric field are joined, then an equipotential surface is obtained. Okay, so this is very important point, that if all the points at same potential in the electric field are joined, then equipotential surface is obtained. If you have like this small q charge, and if you obtain the potential due to charge, and we join them, like for each point v1 we will join them each point, because these all points are equidistant from this and having same potential, so it will like form a spherical surface for a small free charge, and this is your equipotential surface. Okay. The shape of equipotential surface due to a line charge is cylindrical. If you have like line charge here, line charge, so you can see that it has equipotential surface as a cylindrical only, because each point equidistant from it having the equipotential surface. Okay, like these are equipotential only, and it will form a cylindrical like shape. So that is for a line charge only. Okay, equipotential surfaces for line charge, that is in shape of cylinder. And point charge is spherical. Point charge, I already told you that this is spherical equipotential surface for small point charge. Different properties of equipotential surface are given as below. So some properties are also given for equipotential surface. Let's clear the drawing and see what are the like properties. So equipotential surfaces do not intersect each other, as it gives two direction of electric field at intersecting point, which is not possible. So I already told you that electric field lines cannot like cross each other, because it will like show the two directions of electric field at a point. Similarly, electropotential surfaces like equipotential surfaces do not intersect each other, because if they intersect, they will give two direction of electric field. Okay, as your equipotential surfaces are only that point which where we have what, where we have electric field as joint. Okay, see here, if all the points at the same potential in the electric field are joined, then at the equipotential surface, like you will obtain the equipotential surface. So electric field is just dependent on equipotential surface also. Okay, so that is why equipotential do not intersect each other, as it gives two direction of electric field at intersecting point, which is not possible. Okay, so this point is clear. Now see the next point, next property. Equipotential surfaces are closely packed in the region of strong electric field and widely spaced in the region of weak electric field. This is also obvious that if you have like closely packed region of electric field, so you have equipotential surfaces are also closely packed there, because it is like equipotential surfaces are direct proportion to your electric field only. And yeah, you can also like remember one formula, E is equal to V by R here. Okay, this formula you can remember. So you can see that E directly proportional to V only. So equipotential surfaces are like what? Like denser, where electric field is denser. Okay. Now see the next topic, next property. For any charge configuration, equivalent potential surface through a point is normal to the electric field at that point, and directed from one potential surface at higher potential to the equipotential surface at lower potential. Okay. Yes. So this is your very important point, that if you have like any configuration, see here, like you have point charge, and you have like electric field lines like this only. So equipotential surface is what? Just perpendicular to this surface. Okay, because it is joined where you have the same potential at each point. So it means that it will be perpendicular to electric field lines also. Okay, that is why they are perpendicular to electric field lines also at each point. So and also you can observe that the this your equipotential surface are directed from higher potential to lower potential. Okay, like if you have electric field lines like this only. Okay, and you have like potential surfaces are like this. This. Okay. So your this will be at higher potential and this will be at lower potential. Okay, because it is data from higher potential to lower potential only. This will be higher potential. Sorry, this will be higher potential and this will be lower potential. This in this direction the potential will drop. Higher potential and this has lower potential because electric field lines are directed from higher potential to lower potential only. This is the like you have seen in fluid mechanics that your and fluid flow is in the direction of higher potential to lower potential or higher energy to lower energy. That is why here also the electric field lines flow from higher potential to lower potential. Okay. And the fourth point, what is the fourth point? No work is required to move a test charge on an equipotential surface. So this is also very obvious. If you have like equipotential surface here, V is constant each point at each point. So if you move any point charge from here to here, there is no potential difference from this point to this point. So why the work done will be here? Work done is equal to V by your V is only equal to what? Yeah, like what? V by W V is equal to W by Q. Okay, so W is equal to QV only. Okay, so if V is not there, like delta V is not there, this is delta V. So why will be work done here? So work done will be equal to 0. That is why equipotential surface has 0 work done if a test charge move on this. For a uniform electric field, capital E, this is fifth property of your equipotential surface. Okay. So for a uniform electric field, capital E, let along x-axis the equipotential surfaces are normal to the x-axis, that is planes parallel to the YZ plane. Okay. So if you have a uniform electric field, which will let it will be in along x-axis. So if you have less like this electric field lines are like this x-axis along x-axis. Okay. And the equipotential surface will be normal to the x-axis, that is plane parallel to YZ plane. Okay. And YZ plane is what? This is your x. Okay. This will be your like y, and this will be z. So if you talk about any other plane that is YZ plane, so it must be what? Equipotential surface only for this electric field, because it is like perpendicular to this this field only x, and in the xy plane it is perpendicular to xy plane also. So that is why xz plane will become what? Equipotential surface for what? X-axis electric field. So this was telling in this point. So till now we have covered many things today. Like we have studied potential due to dipole, and after that we have also covered potential due to an axial point dipole due to dipole at axial point, and after that we have seen potential surfaces. Okay, some questions also we have taken. So I hope that you like the session today, and if you have any type of doubt or suggestion, so you can comment or tell us. And if you have like uh, if you want one session or private session from us, then you can also tell us or like comment also. So this was enough for today. We will continue our lecture in the next class. Till now, take care and thank you and goodbye.